students, welcome back to our channel Physics Tutorial. Today we are going to start the revision classes for plus 2 physics. The first chapter we are starting today, and this will be helpful for both CBSE and state students. So if you like the video, please like, share and subscribe. Now we can move to the video. Our first chapter is electric charges and fields. In this chapter we are going to study electric charge, conductors and insulators, basic properties of electric charge, Coulomb's law, forces between multiple charges, electric field lines, electric flux, electric dipole in a uniform external field, continuous charge distribution, Gauss's law and its applications. And now we can start with electric charge. So before going to electric charge, have you ever noticed a spark or a crackle sound when we take off our synthetic clothes? Or on a fine day, pass a plastic comb through your dry hair and show the comb on bits of paper. Then what will happen? The comb attracts paper bits, right? Have you ever noticed that? And what is the reason behind all these things? In this chapter, we can understand the reason behind all such phenomena because we will study about static electricity. So here static means the state of rest. We are going to study about electrostatics here. So that will deal with the properties of charges at rest. So then we can understand the reason behind all such interesting phenomena. And now we have to know what is an electric charge. What is an electric charge? Electric charge is actually the property of a matter, right? And when we place an electric charge in an electromagnetic field, what will happen? Which will experience a force, right? So that is actually the property of an electric charge. Electric charge is the property of matter, and due to which it experiences a force when placed in an electromagnetic field. So all these basic things that you should know. And what are the different types of electric charges? Yes, experimentally it is proved that there are two types of electric charges. What are the two types of electric charges? One is positive and the other one is negative. Okay, when we rub two objects, what will happen there? Then there will be transfer of electrons happening, right? So we can say that when we rub, the electrons will be transferred from one body to other body, and the body which loses electrons, that will be becoming positively charged, and which gains electrons becomes negatively charged. That means loses electrons means that will be positively charged, and when it gains electrons, that will be negatively charged. Or we can say that positive charges means there will be deficiency of electrons. That means if there is a deficiency of electrons means that will be positive charge, and if there are excess of electrons, that will be negatively charged. Okay, so this you have to remember. And one more thing is that the unit of charge. What is the unit of charge? That is Coulomb, right? That is the basic thing that you should know. That is Coulomb, that is represented as C. C is the symbol of Coulomb. And what is the charge of electron? That is also, yes, 1.602 into 10 raised to minus 19 Coulomb. That is the charge of electron. So in this electric charges, you should remember these 2-3 points. That is, first one is types of charges, positive and negative. Positive means there will be deficiency of electrons, and negative means excess of electrons, and unit of charge is Coulomb. Then charge of electron is 1.602 into 10 raised to minus 19 Coulomb. So now we can move to the next topic. Now we are going to study about methods of charging a body. So here we have to know that how to charge a body by using different methods. So here we know that the electrostatics we are dealing, that means the electrons will be at rest. Statics means state of rest. So electrostatics means electrons will be at rest. So in the first two chapters we will be dealing with electrostatics, and from the third chapter onwards we will study about the moving charges, that means current electricity. Okay, so here we can see how the material is charged by using different methods. So first of all we have friction. So by using friction we can charge only insulators. So insulators can be charged by using this friction. So the frictional electricity will be produced. So here by using friction we are charging insulators, and by using induction or by using conduction we can charge conductors. So this can be used to charge conductors. Okay, this is very important. And by using friction, how we can charge the objects, that is our question now. Okay, so for that we can consider an example. Here we have a pair of materials. We are taking this glass rod and silk. This is one pair, and suppose we rub the glass rod with silk. So in such a case, rubbing means that actually friction is happening there. Okay, so what happens is that glass rod becomes positively charged and silk becomes negatively charged. How that happens? In the case of glass rod, that when an object is becoming positively charged, when it loses electrons, that becomes positively charged, right? And when an atom or when an object gains electron, that becomes negatively charged. So in this case, what happens, that you have to know. So how it becomes positively charged and how silk is becoming negatively charged. So in the case of an atom, we know that inside the nucleus there will be protons, and outside that outside the nucleus we can see electrons. Okay, and in the case of an atom, this protons and electrons will be equal in number. Okay, so the number of protons will be equal to number of electrons. That electrons will be in the outermost shell. Here we can see outside this is the nucleus, and outside the nucleus we can see the number of electrons. Okay, here also suppose this is glass rod and this is silk. Okay, here this is the outermost shell. So what is the peculiarity of outermost shell? These electrons will be free to move. Okay, and here also we have the outermost shell, and here we can see that in the case of glass rod the number of electrons are lesser than the number of electrons in the silk. Okay, so what happens is that from the glass rod an electron will be moving to silk. Okay, when they are rubbing each other, that transfer of electrons happens, and from glass rod an electron will be moved into silk. So what happens, that glass rod becomes positively charged and silk becomes negatively charged, because this is not that much strong and it is very easy to remove an electron from the outermost shell of glass rod to silk. And here we can see that there are 4 number of electrons, right? Suppose there are 4 number of electrons, means this is more than this outermost electrons in the glass rod. Okay, so this is an example. So this is how that glass rod becomes positively charged and silk becomes negatively charged. And we can see in the case of woolen cloth and ebonite, this is another set of materials that we are rubbing together. So woolen cloth is rubbed with ebonite. So what happens here, woolen cloth is becoming positively charged and ebonite becomes negatively charged. In the same way, here the next set is woolen cloth and plastic rod. So what happens, woolen cloth is becoming positively charged and plastic rod becomes negatively charged. And in the last case we can see ebonite rod. Ebonite is rubbed with polythene. So what happens, ebonite becomes positively charged and polythene becomes negatively charged, right? So just see this, the second one, woolen cloth and ebonite. Here ebonite is becoming negatively charged and woolen cloth is becoming positively charged, right? And in this case what happens, when we are rubbing ebonite with polythene, ebonite becomes positively charged and polythene becomes negatively charged. Okay, so what happened here, we can't predict that which one will be positive or negative. That depends on the pair which one we are taking. Okay, here ebonite, when we are rubbing with polythene, that becomes positively charged, and the same ebonite whenever we are rubbing with woolen cloth, ebonite becomes negatively charged. So that depends on the pair which one we are taking. Okay, so that should be careful whenever we are rubbing 2 objects. That depends on the pair which one we are taking for rubbing. So in such a way the transfer of electrons happens in the case of friction. So in that way the frictional electricity is also produced. That is very important thing that you should remember. and in the case of insulators only we can use this method. Now we have already discussed the type of charging, that is friction. Okay, so friction were used in the case of insulators only. So what are insulators? Insulators are the substances which offer high resistance to the passage of electricity, right? That means it won't allow the passage of electricity through them. Okay, so that examples we have already seen there. Okay, glass, then plastic, nylon, wood, all these were insulators. And here we are going to discuss that induction and conduction. So we have told that induction and conduction are used to charge conductors. Okay, so here you can use any conductor to charge by using induction. So induction is a method of charging because a transfer of charge from one place to another without any physical contact. There will be no physical contact for transferring a charge from one body to another body. So that is in the case of conductor. So here we can take a conductor. Suppose we are taking a neutral metal. Okay, metal we are taking here. See, this is a metal, here it is neutral. Okay, and what we have to do is here we are taking a negatively charged rod, so that we are placing near to this metal plate. Okay, so this is not in contact with the metal plate, and here we are just placing this charged rod. Then what happens here? There is negative charge. So here we know that the similar charges will repel each other, right? So the negative charges will be going to the other end of the metal plate. So here all these will be negative charges, and then automatically the opposite charges, positive charges, will come to this end. So here the positive charge will be residing. So now what we have to do is here we will earth this side, this negative side, right? So this side we have to earth. Okay, then what happens? This negative charges will be going to earth, and then all these positive charges will be filled with this metal. So here we will get a plate like this. All this will be equally distributed. All the positive charges will be equally distributed. So here for getting the positive charges we are taking that oppositely charged metal rod. Here that is negatively charged metal rod we are using to get positively charged metal. Okay, so that is the case of induction. So you just understand that induction is transfer of charge from one place to another without any physical contact. Only that much you have to remember. These things just I told to understand the concept. Okay, and in the next case we have charging by conduction. Conduction is just the transfer of charge from one place to another with physical contact. Here we can see that here we are also taking a same metal, that is neutral metal, and here we are placing this similar charge. Okay, because positive charge if you want to transfer means the same charge we have to keep in contact with the metal. Okay, here we are taking a metal rod which is charged positively and we are placing in contact with the metal, then the charges positive charges will be transferred to this metal. So all these will become positively charged. These are the three types of charging. Okay, so first one we have already told that friction, that means in the case of insulators we are using, and in the case of conductors we are using induction and conduction. Clear? Now we have some properties of electric charges. What are the different properties of electric charges? We have already studied that different types of charges are positive charges and negative charges, and also like charges repel and unlike charges attract each other. Okay, now we have some more properties of electric charges, that is addition of charges, quantization of charges, and conservation of charges. First of all, we can see that what is addition of charges. That means suppose we are having three charges Q1, Q2 and Q3. Q1, Q2, Q3. Any number of charges we can take. Okay. Then how we can find the total charge of the system? Here this is a system containing three charges. Then we have to find the total charge of the system. Then what we can do? The total charge Q will be equal to Q1 plus Q2 plus Q3. That means the total charge of the system will be the algebraic sum of the individual charges. That is called addition of charges. That is, the total charge of the system will be the sum of, or the algebraic sum of individual charges. That is called addition of charges. Next, we have very important property, that is quantization of charges. What is quantization? That means all the electric charge is quantized. That means electric charge will be always quantized. Then how we can write it as? Now we have quantization of charges. This is very important. Quantization means the electric charges are always quantized. That means electric charges can be represented as an integral multiple of charge. That means Q will be equal to plus or minus n into E. Here E is the charge of an electron and n is 1, 2, 3, etc. n. That means that all the charges can be written as the multiple of an electronic charge, that is 1n or 1 electron, 2 electron, 3 electron, etc. That will never be written as 1.5 E, 2.5 E, like that. We can't split the charge into half. Okay, that is, this is always an integral multiple of electronic charge. That is, Q is equal to plus or minus n into E. Here n is equal to 1, 2, 3, etc. Okay, so that is quantization of charge. So that you have to know, electric charges are always quantized and electric charge is always an integral multiple of charge E. Okay, and last one is conservation of charge. What is conservation of charge? For an isolated system, the total charge of a system remains constant. And in the case of that friction we have seen, okay, that is, suppose we are rubbing two objects, then what happens? Then one electron will be transferred to the other. But for the total system, what happens? The total number of electrons and total number of protons will be the same only. Okay, only the transfer of charges is taking place there. So we can say that for an isolated system, the total charge of a system remains constant. That is conservation of charge. So these are the three properties: addition of charges, then quantization of charges, and conservation of charges. For addition, how we can write? In the case of a system, suppose Q1, Q2, Q3 are the charges, then Q will be equal to Q1 plus Q2 plus Q3. And quantization means the charges are always quantized. Okay, electric charges are always quantized and it can be represented as an integral multiple of electric charge, and Q will be equal to plus or minus NE. Okay. Conservation of charge means that for an isolated system, the total charge of a system remains constant. Clear? Now we have very important law, that is Coulomb's law in electrostatics. So how to find the force of attraction or force of repulsion between the two electric charges, that is 2 point charges we are taking, and we have to find the force of attraction or repulsion between the two charges. For that, here we are considering two charges. Suppose Q1 and Q2 are the 2 point charges. They are kept at a distance r between them. Okay, so in between the distance is r, and these two charges we have kept in free space or in vacuum. Okay, now we have to find the force of attraction or repulsion between the two charges. So we can use Coulomb's law for finding the force between them. So according to Coulomb's law, the force of attraction or repulsion between the 2 point charges is directly proportional to the product of the charges and is inversely proportional to the square of the distance between them. So how we can write? According to Coulomb's law, the force of attraction or repulsion, that is F, that is proportional to product of the charges, that is Q1 into Q2. So here we can write F is proportional to Q1, Q2, and which is inversely proportional to square of the distance, that is F is proportional to 1 by R square. Okay, so in that way we can calculate the force of attraction or repulsion between the 2 point charges. So here we can combine the two equations, right? Then what we will get? F is proportional to Q1, Q2 by R square. Then this is only proportionality. Then we have to change this into equal to sign, right? Then what we will do, here we have to multiply with a constant. So suppose k is a constant, then what we are getting, f is equal to k into q1 q2 by r square. Here k is 1 by 4 pi epsilon 0. Epsilon 0 is the permittivity of free space. So epsilon 0 means permittivity of free space, and its value is epsilon 0 is equal to 8.854 into 10 raised to minus 12 coulomb square per Newton meter square. Right? Now we can calculate the value of force in free space. So when these two charges are kept in free space, the equation is found to be 1 by 4 pi epsilon 0 q1 q2 by r square. Now we can calculate the force. Suppose the two charges are kept in medium other than vacuum, or in any medium. If you are placing that, the value of epsilon 0 will be equal to epsilon. That means epsilon is equal to epsilon 0 into epsilon r. Right. Here instead of epsilon 0 we have to substitute epsilon 0 epsilon r, because epsilon is equal to epsilon 0 into epsilon r, and epsilon r is called relative permittivity. Relative permittivity. So epsilon is equal to epsilon 0 into epsilon r. So epsilon r will be equal to epsilon by epsilon 0. This is called relative permittivity. Then we will get the equation as f is equal to 1 by 4 pi epsilon 0 epsilon r q1 q2 by r square. So this is the case of force of attraction or repulsion between the charges when the charges are kept in any medium other than vacuum. Okay. So like that we can calculate by using Coulomb's law. Now we have to remember these points, that means the definition of Coulomb's law. How we can define Coulomb's law? The force of attraction or repulsion between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. That is, if they are kept in vacuum, f will be equal to 1 by 4 pi epsilon 0 q1 q2 by r square, and in the case of medium, f will be equal to 1 by 4 pi epsilon 0 epsilon r q1 q2 by r square, and epsilon is equal to epsilon 0 into epsilon r. Here epsilon r is called the relative permittivity. Okay, relative permittivity, and the value of 1 by 4 pi epsilon 0 is 9 into 10 raised to 9 coulomb raised to minus 2 Newton meter square. Okay, so all these things you have to remember in Coulomb's law. Now we can see how to write this Coulomb's law in vector form, because this is a vector, force is a vector, so that we can represent this in vector form also. Now we have to represent this Coulomb's law in vector form. So in the Coulomb's law we have studied the magnitude of force between the two charges, right? That was F is equal to 1 by 4 pi epsilon 0 q1 q2 by r square, and now we are going to find the vector form of that. So in the case of vector form we have to find the magnitude as well as direction, right? For that we are considering two charges, that is q1 and q2. Here equal and opposite charges we are taking. That means one charge is positive and the other charge is negative. That means the force will be attractive. Okay, so these two charges will attract. So here the distance of separation between the two charges is r, and now we have to find the force acting on these two charges. So first of all we have to know in which direction the force will be acting. Suppose we are finding the force on q1 due to q2. The force acting on q1 due to q2. So in which direction it will act? That means that is a attractive force, right? So force on q1 means this will be acting in this direction, that will be attracting. Okay, so what will happen? Force on q1 due to q2, that is acting in this direction. Clear? And now we have to find the force on q2 due to q1. So what will happen? This will be attracted towards q1, so that the direction of F21 is like this. So always we will represent the force on q1 due to q2 as F12, right? F12 means the force on q1 due to q2, and F21 means the force on q2 due to q1. Clear? So these two are acting in opposite directions. And now we have to find the vector form. In last year we have studied that unit vector is equal to a vector divided by modulus of that vector. Right, that means this is a unit vector. Unit vector is equal to a vector divided by modulus of that vector. Here we want to find this vector. So how we can find vector? Vector will be equal to modulus of that vector into unit vector. Right, so here we have force. So how we can find the unit vector in the direction of these two vectors? First of all, F12 is there. For that we have to find the unit vector, and for F21 also we have to find the unit vector. See here, F12 means the force on Q1 due to Q2. Then the direction of unit vector will be R12. So that will be acting in the same direction. Right. Here also we have the unit vector, that means R21. So that is acting in this direction. Right. So these two are the unit vectors. Now we can find the force on Q1 due to Q2. So how we can write it? The magnitude we can easily write. How? F12 is equal to 1 by 4 pi epsilon 0. The two charges are Q1 and Q2 divided by distance square, that is R square. So 1 by 4 pi epsilon 0 Q1 Q2 by R square is the magnitude. Now we have to get the direction. For that what we have to do? We have to multiply with a unit vector. So this is the modulus of the vector and into unit vector, that is R12 cap. Clear? So vector F12 will be equal to 1 by 4 pi epsilon 0 Q1 Q2 by R square into R12 cap. And in the similar way we can represent the force on Q2 due to Q1. How we can write it? Force on Q2 means F21. F21 is equal to, this is a vector. So first of all we have to write the magnitude of the vector. So what we will get? 1 by 4 pi epsilon 0 Q1 Q2 by R square into unit vector, that is R21 cap. Here F21 we are finding means that unit vector is R21 cap, that we have already marked there. So that we have to multiply. And from these two equations what we can understand? These two are having the unit vectors, right? The magnitude is same but the directions are opposite. That means R21 is equal to minus R12 cap. Right, R21 cap is equal to minus R12 cap means the forces also will be equal and opposite. Right, so how we can write? F21 is equal to minus F12. So that is the vector form of Coulomb's law. F21 is equal to minus F12. And the equation is F12 is equal to 1 by 4 pi epsilon 0 Q1 Q2 by R square into R12 cap. And F21 is equal to 1 by 4 pi epsilon 0 Q1 Q2 by R square into R21 cap. Only that difference is there. And this last equation is very familiar to you, right? F21 is equal to minus F12. What does it mean? Yes, that is equation for Newton's third law. So what we can say? Coulomb's law obeys Newton's third law of motion. Right? That means F21 is equal to minus F12. Now we have superposition principle, or the forces between multiple charges. So how we can find the forces between multiple charges, or what is the principle of superposition? Here we are taking a charge Q. Here Q is placed at the center, and here we can see a number of charges around it, that is Q1, Q2, Q3, Q4 and Q5. They all are at a distance R1, R2, R3, R4 and R5 respectively. Right. Now we have to find the net charge acting on this charge Q. So how we can find? The force on a charge due to number of charges will be the vector sum of forces due to individual charges. So the total charge on the charge Q due to number of charges will be equal to the vector sum of the charges due to individual charges. That means how we can find it? Here we are having Q1 charge, that means the force acting will be F1. So F2, F3, F4 and F5. These all are the forces acting on Q due to these charges. Right. So how we can find? We can take the vector sum of the forces. That means F will be equal to F1 plus F2 plus F3 plus F4 plus F5. If there are n number of charges, we can find the total vector sum of all the forces acting on that. So that is superposition principle. I will repeat that. That means force on a charge due to a number of charges is the vector sum of forces due to individual charges. Clear? Now, electric field. What is electric field? Actually, this electric field is introduced to explain the interaction between charges. So, by using this, we can understand the interaction between two charges. And before going to the concept of electric field, we can just compare it with magnetic field. Magnetic field is very familiar for us, right? If we are taking a magnet and keep a nail or any magnetic material close to that, what will happen? That magnet will attract that magnetic materials, right? Suppose if it is a nail, and that will be showing that attractive property there. Okay, so that will attract, and suppose we increase the distance of the nail from the magnet, what will happen? If we move it away from the magnet, what will happen? That attractive force also will be decreased, right? So there with the presence of this magnetic material or nail, we can understand that how the magnetic force is acting there, or how much is the magnetic field present there. So in a similar way, electric field is also electric charge is also having such a property. If you are placing an electric charge, and if you place another test charge near to that, we can understand the presence of that charge, because electric field is a region around a charge where its effect can be felt. Because if you are placing an electric charge, we can see a region around that charge where its effect will be felt. Okay, so that is called an electric field. So if you are taking a charge, we can call it as a test charge, a source charge. So this is our, suppose this is our source charge Q. Okay, we are placing a source charge, and for understanding the effect of the source charge, we have to place a test charge near to that. Here we can see at a point P, we are placing a test charge Q0, and this test charge will be always a unit positive charge. So if we place this unit positive charge near to this source charge, we can see the effect of, that means the electrostatic force or the intensity of electric field we can find. And for that, we are using the equation E is equal to F by Q. Electric field can be found by using the equation E is equal to F by Q. F is the electrostatic force that we have already found from the Coulomb's law, and by Q is the charge, electric charge. So by using this, force also can be found by using the equation F is equal to QE. So you have to understand the equation, that is E is equal to F by Q. And electric field is the region around a charge where its effect can be felt. It is the region around a charge, it is the region or space around a charge where its effect can be felt. Okay, and E is equal to F by Q. From that we can see F is equal to QE, and unit of electric charge, electric field is, what will be the unit? Newton per coulomb, because F by Q, right? So Newton per coulomb or volt per meter, and this is a vector quantity. So by using this equation, we can calculate the electric field also. And suppose we are placing a source charge here, and at a distance we are placing this point P. Okay, that test charge is also kept here, and we told that this test charge will be always a unit positive charge. Okay, and suppose this source charge is positive, then how we can find the direction of this electric field? Because this is a vector quantity, right? So we have to find the direction also. So how we can find? If Q is positive, what will happen? This is also positive, so these two similar charges will repel. That means the electric field will be away from the source charge. Okay, so in such a case, if source charge is positive, then the electric field will be away from the source charge. Okay, and if the source charge is negative, then what will happen? If the source charge is negative, means here Q will be negative. So what will happen here? Yes, this is positive and this is negative, so that will be attracted, right? So that will be towards the charge, so that will, electric field will be moving towards the charge. Here we can see that direction will be towards the charge, and if it is positive, that electric field will be away from the charge. So this concept you have to understand. So in this section we are just understanding that a new concept, that is electric field. It is the region around a charge where its effect can be felt, and E is equal to F by Q. Also F is equal to QE. Right, unit is Newton per coulomb or volt per meter. Here we are placing a source charge, and for testing this field we can place a test charge, that is a unit positive charge. And if the source charge is positive, the electric field will be away from the charge, and if the source charge is negative, that will be attracted. That means electric field will be towards the charge. So all these points are very important that you just understand. So this is needed for our next derivation part also. Okay. Now we have to find the electric field due to a point charge. So here we are considering a charge plus Q, and a test charge is kept at a distance r from the charge. Okay, that means Q0 is the test charge. So what will be the direction of electric field here? Here these two are positive charges, so that will be away from this positive charge. Right, so here the direction of the field is marked here. And how we can find the force experienced by Q0? By using Coulomb's law we can find that. So what is the equation for Coulomb? Equation of Coulomb's law, that is F is equal to 1 by 4 pi epsilon 0 Q1 Q2 by R square. Right, so here we have to find the electric field, so that will be equal to E is equal to F by Q0. So first of all we can find F and divide it with Q0. So how we can find? F is equal to 1 by 4 pi epsilon 0 Q0 by R square. Right, here that will be equal to 1 by 4 pi epsilon 0, then Q0 by R square. Clear? Then whole divided by Q0 we have to do. So by Q0 means what we will get? This Q0 and Q0 will get cancelled. Then E will be equal to 1 by 4 pi epsilon 0 Q by R square. So very easily we can find the equation for electric field due to a point charge. So here we are getting the equation of field as E is equal to 1 by 4 pi epsilon 0 Q divided by R square. So this is the equation. Right, now we are just here we are just using Coulomb's law to find the force and divide it with unit test charge. Okay, Q0, that is F by Q0 we are finding. The charges are Q and Q0. These two are positive charges. So Q0 by R square whole divided by Q0. So we are getting it as E is equal to 1 by 4 pi epsilon 0 Q by R square. So you have to remember the equation. Clear? Now we are going to discuss electric field due to a system of charges. Now we have studied the electric field due to a point charge. Right. So what was the equation for that? E is equal to 1 by 4 pi epsilon 0 Q by R square. Isn't it? Now we have to consider 4 charges. Here any number of charges we can consider. We are taking only 4 charges, that is Q1, Q2, Q3, Q4. Okay, that is Q1, Q2, Q3 and Q4 are the 4 charges, and here we can see a point O where we are placing this test charge. Okay, then we can see the electric fields corresponding to Q1, Q2, Q3, Q4, that is E1, E2, E3 and E4, because these two are the positive charges, so that will repel. Okay, so that will be the direction will be away from the point charge. Right, so here that O is the origin. Here we are placing this test charge, and here we are getting all the electric fields, the directions of the electric fields as shown in the figure. And the position vectors, that means the distance between this Q1 and this test charge is taken as R10, R20. Here we have R10, here R20, then this is R30, R40, like that. Okay, so these distances are taken as R10, R20, R30 and R40. Now, how we can find the electric field due to a system of charges? It is very easy to find the electric field of a system of charges, because the electric field due to system of charges is the vector sum of the electric fields at the point due to individual charges. So here also we have to find the vector sum of the fields at the point due to individual charges. So how we can find? E will be equal to E1 plus E2 plus E3 plus E4. Okay, if there are n number of charges, we can take it as E1 plus E2 plus E3 plus etc. plus En. Like that we can find. So here we are finding the values of E1, E2, E3 and E4. Then we can substitute. So what we are getting? Here we have the values of E1, that is E1 is 1 by 4 pi epsilon, then Q1 by R10 square, right, into R10 cap, because vector sum we have to take. So that is Q1 by R10 square into R10 cap, plus in the same way we have to find E2, E3 and E4. So Q2 by R20 square into R20 cap, plus Q3 by R30 square into R30 cap, plus Q4 by R40 cap. So that is the electric field due to a system of charges. So if you are taking a system of charges, we have to take the vector sum of the electric fields at the point due to all the individual charges. Clear? Now we have electric field lines. So electric field lines are an aid in visualizing electric field, so that we can use to visualize the electric field. Okay. And in uniform electric field, the lines of force will be straight, and for non-uniform electric field we can see the lines of force will be curved. Okay, also the tangent to the line at any point gives the direction of electric field intensity. So that is a peculiarity of that. That means the tangent drawn to the line at any point gives the direction of electric field intensity. And we have some properties of electric field lines that you should know. Okay, that means electric field lines will start from positive charge and will end at negative charge. That is very important. In the case of a positive charge, here we can see if we are placing a charge plus Q here, we can see the field lines will be going away from the positive charges. Okay, that means the electric field lines start from positive charge. So always the field lines will be going outwards. So that is the case of a positive charge. In the case of negative charge, what will happen? That will be it will end at negative charge, means the inward, that means the arrow will be inward here. Okay, so the lines of force will be coming towards the negative charge. So if we saw such a picture, we can understand the difference between positive and negative charges. Here it is going away and it is coming towards this charge. Okay, and electric field lines of a positive charge are radially outward and that of a negative charge are radially inward. Okay, that we have already told now. And electric field lines do not form closed loops. Here we can see that it will never form closed loops. And in charge free region, field lines are continuous. Okay, and they will never intersect each other. If they are intersecting, means there should be two directions for that electric field. Okay, so it is not possible. Because of that, it will never intersect. That means two field lines will never intersect. And in the case of uniform field, that will be parallel. That means equidistant and same direction. And in uniform electric field only, right? And here we can see two charges, that means positive charges. If they are kept together, how we will get the field lines, that we can see here. See this, here we have two positive charges. So here the positive charges means the field lines will be radially outward. Okay, so here we can see the positive charge is kept here, and near to that we have kept another positive charge. So these will be repelled each other. Okay, similar charges will repel. So the shape of the field line will be like this. So here we have that all the charges, all the field lines radially outwards. Here also it is like that. And suppose we are considering positive and negative charges, then what will happen? Here we have the picture. Okay, here we have a positive charge and here negative charge. So the field lines will start from positive charge. So here it is going towards negative charge. Okay, and here it is going outward, and in this side it is going coming inward. Okay, so like that we will draw the dipole, that is positive and negative charge. The field lines will be like this. Now we have to find electric flux. So for that we are considering a uniform electric field. Here we can see a uniform electric field, and we can consider a small area ds in that. this is the small area. Okay, so this area, and we draw a perpendicular to this ds. So here this is the area, and for this we draw this perpendicular. Okay, and here we can see that theta is the angle which is making with the normal to the electric field. Okay, so here theta is the angle between this normal, and that means normal to ds, and with the electric field, this is the direction of electric field. So this is theta, and now we have to find the electric flux through this. Here, what is electric flux actually? That is the number of electric field lines passing normal through a surface. That is the number of electric field lines passing normal through a surface. So we have to find the number of field lines passing normal through this surface. For that we can use the equation phi is equal to integral E dot ds. Okay, so E dot ds means E is the uniform electric field, and ds that small area we are taking here. So here we are giving this E ds is equal to E ds cos theta. That is the equation for finding electric flux. So electric flux is the number of electric field lines passing normal through a surface, and phi is equal to E ds cos theta. Here theta is the angle between E and normal to ds. Okay, and what will be the unit? Unit is Newton meter square per coulomb, and this is a scalar quantity. Now we are going to electric dipole. Electric dipole means two poles will be there. Right, here we are considering two charges, that is equal and opposite charges. Here minus q charge and plus q charge, they are separated by a small distance 2a. So this system is called electric dipole. So electric dipole is a pair of equal and opposite charges separated by a distance. That is a pair of equal and opposite charges separated by a small distance is called electric dipole. So the distance is taken as 2a here. Alright, and the total charge of the system, what will be the total charge of the system? Here we have minus q and plus q, they are equal and opposite. So total charge will be 0. Okay, and here we can see P. P is the dipole moment of the electric dipole. So electric dipole moment is the product of magnitude of one of the charges and the distance between them. So here we can write P is the electric dipole moment, and we can take it as the product of one of the charges. Here we are taking minus q and plus q. So any one charge we can take q, okay, into the distance between the charges, that is into 2a. So how we can define dipole moment? Dipole moment is the product of magnitude of one of the charges and the distance between the charges. Here q is the magnitude of charge, then 2a is the distance between the two charges. Then what is the unit of electric dipole moment? Here q and a is there, right? So what will be the unit? Coulomb centimeter, because charge of q is unit of q is coulomb, then a is meter. Okay, so coulomb meter is the unit of dipole moment. Then this is a vector quantity. Now we have one more small term, that is non-polar molecules and polar molecules. Have you heard about non-polar molecules and polar molecules? Here we have non-polar means in the case of non-polar molecules, the centers of positive and negative charges will be at the same place. That means there will be no difference between the positive and negative charges. So the centers of positive and negative charges will be the same place. Then what will happen? Here the dipole moment will be 0, right? Because there is no difference between these two charges. So in this case we can say that the dipole moment will be 0. This is very important to understand. Okay, so in case of non-polar molecules, the dipole moment will be 0. For example, carbon dioxide, then CH-4 and all, it is having the dipole moment 0. So CO2 and CH4 are the examples for non-polar molecules. And when we consider this polar molecules, we can see that the centers are separated by a distance. In this case, the centers of negative charges and positive charges are not coinciding. Therefore, they have a permanent electric dipole moment. That means the polar molecules are having a permanent dipole moment. The example is H2O. So this is the example for polar molecule. So we have to understand what is electric dipole, then electric dipole moment, then its equation and unit, then polar non-polar molecules. So what is electric dipole? Electric dipole is a system of equal and opposite charges separated by a small distance. Electric dipole moment is the product of magnitude of one of the charges and the distance between the charges. Only magnitude we are taking there, so no need of that negative or positive. Okay, and the equation is P is equal to Q into 2A, and the unit is coulomb meter. Then polar and non-polar molecules. In the case of polar molecules, the positive and negative charges, the centers of positive and negative charges coincide. There will be no dipole moment, and the examples are CO2 and CH4. And in the case of polar molecules, they have permanent dipole moment because the positive and negative charges do not coincide. So dipole moment will be there, and example is H2O. Now we are going to derive the electric field due to a dipole along the axial line. So along the axial line, what will be the electric field due to a dipole, that we are going to derive. In the next case, we will derive an equation for electric field due to a dipole along equatorial line. So now we can consider an electric dipole and a point along the axial line. So we will find the total electric field due to this dipole acting on point P. Okay, so first of all we can consider the diagram. Here we can see a dipole, that is two charges, plus Q charge and minus Q charge. They are separated. This is plus Q, that is separated by a distance 2A. So from the center, this distance will be A and this will be also A. Clear? And now we are considering a point P at a distance R from the center of the dipole. So this is the center of the dipole. From the center to P, this is the point P at a distance R here. Okay, and we are finding the electric field at this point P due to this dipole. So how we can find the electric field at P? So two charges are here, right? Plus Q charge is there, minus Q charge is there, and here we are placing a test charge. At P we are placing a test charge, and we have to find the electric field at P due to this plus Q charge and also the electric field at P due to minus Q charge, because these two charges will act on that charge. Okay, so that we will find and we have to add it together for getting the total electric field at point P. Now we can consider here the field directions are given. So here we have a positive charge. Test charge is always a unit positive charge, right? And here we are having positive charge, means the direction of the field will be, yes, outwards. Okay, that will be repelled. So these two similar charges, they will repel each other. And what about this negative charge here? Minus Q charge is there. That means here the positive charge and negative charge will be attracted. So that means the direction of the field will be towards this negative charge. So E minus Q is shown here. Now we can find the electric field at P due to plus Q charge. So how we can find the electric field at P due to plus Q charge? Due to a charge, we have derived the equation for finding the electric field. What was the equation? E is equal to 1 by 4 pi epsilon 0 Q by R square, right? So in this case we are finding E plus Q. So the equation becomes 1 by 4 pi epsilon 0, then Q by, what will happen here? The distance between these two, that means the point P and plus Q charge. This distance we have to find. So here from the center to point P we have R, okay, and here this distance is A. So what will be the total distance between P and plus Q charge? That will be R minus A. Clear? So we can write R minus A the whole square, and that will be in the direction of P. The direction is as shown in the diagram. Okay, and what about the electric field at P due to minus Q charge? So how we can find the electric field due to minus Q charge? Here we have 1 by 4 pi epsilon 0 Q by, that distance we have to find. What will be the distance here? How we can find the distance between P and minus Q charge? Here we have R and this distance is A. So what will be the total distance between P and minus Q? That will be R plus A. Clear? So we can write it as 1 by 4 pi epsilon 0 q by r plus a the whole square, and the direction is as shown here. Okay. So we have two equations, that is E plus Q and E minus Q. Now we have to find the total field. How we can find total field? That is E plus Q plus E minus Q. So here it is negative, right? Minus Q charge is there. That means E plus Q minus E minus Q we can do. So we can substitute that values. So what we are getting? E is equal to 1 by 4 pi epsilon 0 q by r minus a the whole square minus 1 by 4 pi epsilon 0 q by r plus a the whole square. Now the common things that we can take outside, what we will get? Q by 4 pi epsilon 0 is common. Okay, so that we are taking outside. Then within the bracket 1 by r minus a the whole square minus 1 by r plus a the whole square. Now we have to simplify. Clear? Now we can simplify the equation, that is E is equal to q by 4 pi epsilon 0 and 1 by r minus a the whole square minus 1 by r plus a the whole square. Now we can take the LCM, that is r square minus a square the whole square, and then what will come here? R plus a the whole square minus r minus a the whole square will come, right? So r plus a the whole square means that is a plus b the whole square. So how we can write? R square plus 2ra plus a square minus of this r minus a the whole square, that is r square minus 2ra plus a square. So we are taking the form of a plus b the whole square and a minus b the whole square. Okay, so a square plus 2ab plus b square and a square minus 2ab plus b square. Now we are getting this. Now we can cancel some terms, right? Here r square and r square will get cancelled. Here a square and this is negative, right? So here this a square also will get cancelled. Then what is remaining here? That is 2 into what is coming here? 2ra. That means 2ra, this will be plus 2ra. So 2 into 2ra divided by r square minus a square the whole square. So this term is also there, right? Then how we can write it? E is equal to q by 4 pi epsilon into epsilon 0 into 4ar divided by, because we are just multiplying this, 4ar divided by r square minus a square the whole square. Now suppose this r is very much greater than a, because a is the half of that dipole, right? That is very small length. So if r is too much greater than a, we can neglect this value of a. So how we can write the equation? E will be equal to 1 by 4 pi epsilon 0, because r is very much greater than a, then we will neglect this a. Then 1 by 4 pi epsilon 0, how we can write? 4aq divided by this q we are writing here. So 4aq divided by r cube, because this one r will get cancelled. Then we are getting the equation like this. And we have studied that 2aq is equal to electric dipole moment P, right? So can we substitute for 2aq here? If you are substituting 2aq is equal to P, what we will get? 1 by 4 pi epsilon 0 will be in the same way. Then 2 into P, right, divided by r cube P, because P is equal to 2aq. So 2 into 2aq we can write here. So 2 into P divided by r cube. So this is the equation in the case of electric field due to an axial line on the electric dipole. Okay, so these are the equations. Should I repeat here? What we did is just we are finding the electric field due to plus q charge and minus q charge, and then we are just simplifying the equation. Okay, we have to add the equation, then we are just simplifying here, and then we are substituting the value, that means 2aq is equal to P. So that will be equal to electric dipole moment. Then we will get the final equation as E is equal to 1 by 4 pi epsilon 0 2p by r cube. This is very important equation, you should remember. This is along the axial line, that also you should remember. In the next case we will derive the equation for electric field intensity in the case of equatorial line. Clear?